Welcome back to my course Aspects of Biochemical Engineering. Now, we are discussing the air sterilization process. Today, I am planning to discuss some problems, the numerical problems on air sterilization process, designing of air filter. Now, in the last lecture, you can remember I tried to discuss that what are the different processes through which we can remove the microorganisms or kill the microorganisms. There are three different processes we have. One is called sterilization, and there is the thermization, and there is pasteurization. What is sterilization? Sterilization, either you kill the all microbes present in the particular media or air, and thermization, you just reduce the load of total microbial population, and pasteurization is mainly we target for pathogenic microorganisms. Now, in the fermentation industry, as I told you, sterilization plays very important role, because we want to grow our desired organism. As we know that atmosphere, we have lot of different type of microorganisms, they are present there. So, if you allow those organisms to interfere in the process, naturally our purpose will not be served. So, we shall have to maintain the sterile conditions, and we observed that most of the biochemical industry, they are operated aerobic fermentation. They use the aerobic fermentation process. Now, in the aerobic fermentation process, major drawback is the dissolved oxygen concentration, because your microorganism can take the oxygen which is dissolved in the media. They cannot take the oxygen which is present in the air. So, we shall have to pass the air. Now, we know the air comprises of lot of bacteria, lot of different type of microorganisms. So, if you just purge the air through the media, there is every possibility lot of contaminants may grow in the media. So, we shall have to sterile the air, and also the media that is required, that is also to be sterilized, and also we shall have to sterilize the vessel in which the fermentation take place, also the pipeline and other things where the sample is to be drawn, everything is to be sterilized. So, we observed two major concerns. One is a major source of contamination, one is the air, another is the media. Now, in the last lecture, I tried to discuss how the air sterilization process can be worked out, and I discussed the different way we can sterilize the air. One is heat, one is by using electromagnetic waves, or by using germicidal spray. So, whenever we talk of air, then we find two type of air. One is moving air, and there is stagnant air. For stagnant air, we usually use UV rays, or we use the germicidal spray, because suppose particularly I can give the example in the cheese making industry, that we need a big room for the cultivation of curd. So, naturally curd is usually formation take place in open vessel, and the room should be sterilized, and that we put some kind of chlorination of this room, so that air is free from the contaminants. But a question comes in case of moving air, how the moving air we can remove. So, there are heat and that filtration, two kind of devices can be used for removing the microorganisms present in the air. Now, when we use the heat, naturally that when you increase the temperature, the protein present in the inside the organism, they will be denatured. As soon as they will be denatured, then the biochemical activity of the organism will be lost, and your organism will be killed. So that is, but one problem with the heat in case of air, but air is a non-conductor of heat. So, naturally that is not good media for air sterilization. So, it has been found that maybe that filtration is a device through which we can remove the contaminants present in the air very easily. Now, in filtration also we have found different types of filter. We use the fiber type of filter, we have membrane type of filter. Now, in case of fiber type of filter, the organisms they are entrapped in between the fiber. Now, the fiber, as for example glass wool fiber, if you use, then if you compress it, then when you compress it, we will find that pore size will decrease. So, as per our requirement, then we can design the air filter. Now, there are different principles involved for removing the particulate matter by the filtration that I discussed in the last class, and we have come across one parameter, that overall collection efficiency. This can be theoretically estimated, as well as this can be estimated on the basis of the correlation between the single fiber correlation we have on the flow characteristics of the fluid, that we can find out the overall efficiency of the process, and that we can correlate with the single fiber efficiency. From single fiber efficiency we can find out the thickness of the air filter. Now today we want to discuss some kind of problem that on this air sterilization process. First, let us discuss. Now, it is required to provide 20 cubic meter fermenter with air at a rate of 10 cubic meter per minute for a fermentation lasting for 100 hours. The air contains approximately 200 microorganisms per milliliter. From an investigation of the air material, the filter material to be used, the optimum linear velocity was shown 0.15 meter per second, at which the K value is 1.535 centimeter inverse. Calculate the dimension of the filter if acceptable degree of contamination 1 in 1000. Now, here I forgot to mention one particular one important thing, that when you design any kind of air sterilization or medium sterilization process, we consider that what is the level of sterility we are going to maintain. Now, level of sterility we can maintain in different way. As for example, one we can 1 in here 1 in 1000. Am I right? That means out of 1000 organism, that 1 by 10 that organism should be present, 1 in 1000. So, I can do the sterilization on the basis of 1 in 1 million, 1 in 10 million. So, more when you want more critical sterilization conditions, then our sterility will be more high, because 1 in 10 million, 1 in that kind of, if sterility is not that important, that you can reduce that 1 in 1 million, 1 in 1 lakh, like this we can do that. So, here 1 in 1000 is mentioned here. Now, we have in the last lecture I have shown you that thickness of the filter that can be correlated with the like this, ln n by n0 equal to k into x. Now, how you calculate the air, how much organism present in the air, how you can calculate. And let me show you that if you look at the problem, what is we have 200 microorganisms per cubic meter, and it is flowing at a flow rate of 10 cubic meter per minute. So, and this is lasting for 100 hours. So, if you want to find out per hour, it will be 10 into 60, then the cubic meter per hour. Then if you multiply this, then you will find the how much volume of air is there. Then if you know, this is like this. If I calculate 10 cubic meter, am I right? 10 cubic meter per minute. So, if you multiply it with 60, because one hour is equal to 60, then this we can write like this, then it will be very easy. Though we have 1 by minute. this is 10 cubic meter per minute. Am I right? So, how you can convert it into per hour? This is 1 hour equal to 60 minutes. So, this minutes will cancel. So, 10 into 60 you can do that, and 100 hours, how much volume will be there? You multiply it by 100, then you will get the total volume. Now, per cubic meter how much microorganism present? 200 microorganisms. So, you multiply it by 200, you will get the total number of microorganisms in the air. So, this is exactly what we have calculated. You can see it. Then this is the inlet, and what is the microorganism we are targeting? 1 in 1000. That means 10 to the power minus 3. 1 in 1000. So, how we can write? 10 to the power minus 3. Am I right? So, what is the formula? ln n by n0 equal to k into x. Am I right? Now, n value already we know that 10 to the power minus 3, that we put it here. This is the total number, this is n0, and this is k value. So, we can easily find out the what is should be the filter, what is the length of the filter we can use. This is 15.12. It is not very difficult, you can easily do that. Now, let us consider the second part, that what is the cross section area of the filter is given by the flow rate, the linear velocity. The cross section, how you can find out? Pi r square. So, r is 0.15 meter. So, we can easily find out that this is the per area. Now that where I am solving the above parameter, then we can find out r equal to that, then we can find out the r equal to that 0.58. Now, so the cross section of the filter is coming about this radius is 0.59 meter and length is this. That we can easily calculate, that how we can do the calculation of this particular, because I hope you understand that, because how we have calculated, because you know that we know the flow rate. Flow rate we know. Flow rate is what? Flow rate is cubic meter per minute. Am I right? Now, if you divide by the velocity of air, then obviously we will get the cross sectional area. What is the velocity? Velocity is meter per minute. Am I right? So, minute will cancel, and 1 meter will cancel the square. So, it will be area. So, we can easily do that. So, this is how we can calculate this radius and the length of the air filter. Now, next problem is that for efficient operation of the filter is dependent on the supply of air at optimum linear velocity. If the air filter increases or decreases, the value of k decreases, resulting the loss of filtration efficiency. Consider the previous problem, that so we considered whatever data we have in the previous problem. If the linear air velocity dropped to 0.03 meter per second, the value k declines to 0.2 centimeter inverse. That calculate the number of organisms would enter into the filter in 1 minute at the reduced flow rate, and operation conditions are same as mentioned in the previous problem. Now, how we can solve that? Now, the linear velocity is what is 0.03, this is 0.0 meter per second. The amount of air entered in 1 minute, we can easily calculate it, multiplied by 60 per minute, then pi r square. So, you know that you can find out the amount of that radius is 0.59. So, you can easily find out how much organism is entering into the system. Then the amount of air entering entering in the filter is 1.59 we find out that 1.98 cubic meter. Now, the air contains 200 cubic meter 200 microorganisms per cubic meter. The total number of microorganisms entering would be how much? So, this we know that this volume. So, we can easily find out the N0 value. Now, if you know the N0 value, we know N value. N value we can easily find out that what is the how much organism will leaving the filter. So, 90 as the microorganism was entered the fermenter 1 minute at the decreased air flow rate. So, this we can do it very easily. Now, let us try to solve some other problem that determine this is the design of the air filter. Design the length of the glass wool 5 filter required to reduce the concentration 10 to the power 8 of its origin previous value. That means, what I want to tell that N by N0 that is 10 to the power minus 8 the original value that that is given there. Now, df is the diameter of the fiber is 19 micron, the filter diameter is 1 meter, the alpha is the solid fraction or filter fraction. Solid fraction means I told you that 1 minus alpha is equal to void fraction. Void fraction means free space. Alpha is the how much that filter occupied in the filter, that in the how filter material how much volume is occupied. Then dp is the 0.5 microns and superficial velocity 10 centimeter per second, air viscosity 2 into 10 to the power minus 4 gram per centimeter per second, and particle density 1 gram per centimeter cubed, and diffusivity is 2.73 into 10 to the power minus 7 centimeter square per second. So, these are the different problem is given. So, it is so we shall have to, so we can consider this problem like this. This is suppose this is the air filter and this is the air filter that we have. We know this is we have the air filter like this. So, we pass air in and this is air out. So, here we know the flow characteristics of the air. What is the diameter of the filter, what is the velocity of the air viscosity, all these things, particle diffusivity, everything know. So, we shall have to find out what is the length of this air filter. To get this value n by n0 will be 10 to the power minus 8. Am I right? Let us see how we can solve it. Now, first we shall have to calculate the Reynolds number. Or how we calculate the Reynolds number? This is the diameter of the filter and this is the velocity that so Reynolds number equal to du rho by mu. Am I right? So, that u is the velocity that we can put it here, and this is the rho value, that is the density, and this is the viscosity, and this is the void fraction. So, we will get the Reynolds number like this, assuming the air density is 1.2 into 10 to the power 3 gram per milliliter. Now, the Smith number is equal to mu by rho into dBm. dBm is the diffusivity of the air. Now, mu value is given here. This is mu is the viscosity of the air, and rho is the density of the air, and the diffusivity of the air is given here. So, we can easily calculate what is the Smith number. Then we have the correlation that Peclet number equal to Smith number into Reynolds number. So, we have already found out what is the Smith number and Reynolds number. So, our Peclet number will come 1.5 into 10 to the power 5. Now, that that if you look at this figure, that here we have the correlation inner in P Piclet number to the power 1 by 3 into the Reynolds number 1 by 18. This is correlated with the overall collection efficiency, NR and Piclet number. So we can find this, and from this curve we can find out this particular value. Now if we find out this value, then we can find out from this, we can find out the eta 0 value. Let us see how we have solved this. Now here we have NR. NR is what? A geometrical ratio. It is the diameter of the particle by diameter of the fiber. This is we have. The Piclet number already we have determined. This is the Piclet number, and this is the Reynolds number we determined. So this is coming about 2.3, and so you have from the figure you have this is NR into, you can write N P to the power 1 by 3 in RE to the power 1 by 18. So this is correlated with eta 0 in R and in PE. So if you have curve like this, so if you know this value, I can find out this corresponding value. So N0 NR P in PE can be estimated from the plot for this versus this. Okay. Now we have done this, and we find that this value is equal to that 2 into 10. Now from that we can find out what is the eta 0 value. Eta 0 is the overall collection efficiency, and we know that single fiber efficiency is eta alpha is eta 0 1 plus, for if alpha value lies in between 0 to 0.1. So here alpha value is 0.033. So it is lies in very much in between that, and so we can find out the single fiber efficiency. Once we find out the single fiber efficiency, now we have the correlation of with the single fiber efficiency and the length of the filter, because I was talking about this filter length. Am I right? This is the length of the filter that we have. This is we call it L. So L can be related with this. This is like this. So here pi we know, diameter of the fiber you know, alpha we know, that the solid fraction, and eta alpha we know, N1 N2 you know. The N1 is the final cell mass concentration, and N2 is the incoming cell mass concentration. From that we find out the length of the air filter is coming about 14.65 centimeter. So this is we can easily find out that we can easily design the what do you call that, that air filter, what will be the thickness to get the desired amount of sterility of the air. Now another thing I want to raise here, that suppose in the biochemical industry we have two vessels, one is inoculum, another is production fermenter. Am I right? Now usually the inoculum vessel, suppose this is 1 cubic meter, and usually this size, this usually the 5 to 10%, that means 0.5 to this. If it suppose I can tell you that if the capacity is capacity of production fermenter 200 cubic meter, the inoculum volume will be how much? It is 10 to 20 cubic meter. Okay. Now naturally the air requirement for the small fermenter will be less as compared to the bigger fermenter. Now question comes, how we will design our air filter, because I have already shown you that that for inoculum vessel we can have this, we can horizontal, this kind of things we can have, we can pass the air in and air out, and we can find out the area like this. Now when you go for this is inoculum vessel IV. Now when you consider the production fermenter, Now, naturally it is 10 times higher, 5 to 10 times, and if you increase the 5 to 10 times, then particular surface area will increase very much, and if you increase surface area, there is the operational problem. Now, question comes that how you can reduce, we can make the things very compact, because this we can make the things very compact. How you can make the things very compact? Suppose inside this air filter, if we have some cubical arrangement like this, we can always have a cubical arrangement like this. So, we can increase the surface area, am I right? We can increase the surface area. So, here we can pass air, we can take out the air like this. So, this is we can do in two ways. Otherwise, one is we can put it in and we can take it out like this, or we can take it in and from inside you can take it out. So, in that way we can increase the surface area and make the things very compact. So, this is how you can make the things very compact in case of bigger fermentation process. So, so another one issue I want to take into consideration, that in the industry we use the glass wool fiber. But that we know the glass wool fiber is very costly as compared to cotton or jute fiber. But question comes, why we go for glass wool fiber? The reason is that glass wool fiber, it can be reused again and again, we can sterilize again and again, and cotton and jute fiber, it is very particularly, I can tell you in case of jute fiber, that if you regenerate the jute fiber again and again, it will be becoming fragile. So, you cannot use that. So, and another problem is that when you pass air through a filter, there will be some kind of resistance that that on the flow of the air filter. As there is a resistance, there will be some kind of friction. As there is a friction, there is the heat generation take place. Now, in case of jute and cotton fiber, it can catch the fire very easily, but in case of glass wool fiber, it can, the fire temperature is quite high. So, in that way we find the drag coefficient for a particular Reynolds number in case of glass wool fiber is much less as compared to that jute and cotton fiber, and we find that drag coefficient, since it is more in cotton fiber. So, every possibility that cotton and jute fiber can catch fire, that is why we cannot use. So, in conclusion, I want to tell you that I try to discuss the air sterilization process, which is very important part of the any kind of fermentation industry, and what we are basically targeting, that we it is very difficult to get the 100% sterility of the air. What we can do, 1 in 1,000, 1 in 10,000, 1 in 1 lakh, 1 in 1 million, 1 in 10 million. That means out of 1 million organisms, you are allowing 1 organism can percolate through the filter. Then, because 100% that sterility, to find out that what should be the exact thickness of the air filter for 100% sterility is very difficult to achieve. So, in the air filtration, we always means medium filtration, we always consider that how much organism is allowing out of how much initial input. So, on the basis of that, we can do the design of the air filter. I discussed that how you can discuss the thickness of the air filter, both on the basis of flow characteristics of the fluid, also by using that kind of equation that we have, that ln n by n0 equal to k into x. From that we can find out, that is called log penetration theory. From that we can find out the thickness of the air filter. Thank you very much.